Welcome back students to the part 2 of today's session. In this module, we'll be discussing about the rounding off. So there are certain rules for rounding off the numbers. The first one is when the number to be dropped is less than 5, the preceding number remains unchanged. For example, the number 2.222 when rounded off to 3 decimal places will become 2.22. Since the digit dropped 2 is less than 5, the previous digit, which is marked in red, will remain unchanged. The second rule is that when the number dropped is greater than 5, 1 is added to the preceding number. For example, in the number 2.227, the number dropped is 7, which is greater than 5. So you have to add 1 to the previous digit 2, which is marked in red. Hence, the number after rounding off will become 2.23. The third rule is when the number dropped is equal to 5, there are certain rules to be followed. That is, if the preceding number is even, then it remains unchanged. For example, in the number 2.2225, the digit dropped is 5 and the digit which is before the dropping digit is 2, which is marked in red. Since 2 is even, it remains unchanged. So after rounding off, the number becomes 2.222. The next rule is if the dropping digit is 5, then if the preceding number is odd, then 1 is added to it. For example, in the number 2.2235, the number dropped is 5 and the number preceding the dropping digit is 3, which is marked in red. Since 3 is odd, 1 must be added to 3. So the number becomes 2.224. Let us discuss some examples and calculate the rounded off values. Suppose if the number is 134.56, which must be rounded off to 4 significant figures, then you have to select the first 4 digits in the measurement. So selecting the first 4 digits, you will get 134.5. So the dropping digit is 6, which is greater than 5. So 1 must be added to the previous digit. So the rounded off number becomes 134.6. In the next example, 33.57, which is rounded off to 2 significant figures, we get 33 and the dropping digit is 5. Since the digit 3 before the dropping digit is odd, we will have to add 1 to this 3. So the rounded off number becomes 34. In the example 24.07, which is rounded off to 3 significant figures, the dropping digit is 7, which is greater than 5. So we have to add 1 to the previous digit. So the rounded off number is 24.1. In the number 134.45, which is rounded off to 5 significant figures, the number remains as such and the rounded off number is 134.45. In the example 134.63, which is rounded off to 4 significant figures, the dropped digit is 3, which is less than 5. So the previous digit remains unchanged and the rounded off number will be 134.6. In order to clear the confusions in rounding off, initially we must convert the number into its scientific notation and then round it off to the required number of significant figures. For example, in the number 1539, when expressed in scientific notation, becomes 1.539 into 10 raised to 3. If it is rounded off to 3 significant figures, the number dropped is 9, which is greater than 5. So we have to add 1 to the previous digit 3. So the number becomes 1.54 into 10 raised to 3. Remember that 10 raised to 3 is insignificant in calculating the total number of significant figures. Another example is 0.007362. When expressed in scientific notation, becomes 7.362 into 10 raised to minus 3. If it is rounded off to 3 significant figures, the digit dropped is 2, which is less than 5. So your final answer after rounding off will be 7.36 into 10 raised to minus 3. There are certain rules for determining the uncertainty in the results of arithmetic calculations. For example, suppose if length is given by 16.2 plus or minus 0.1 centimeter and breadth B is given by 10.1 plus or minus 0.1 centimeter, where 0.1 centimeter is the error in the calculation or measurement of length and breadth. When converted into percentage error, this becomes 16.2 plus or minus 0.6 percentage for length and 10.1 plus or minus 1 percentage for breadth. Suppose if you are asked to calculate the area by multiplying length and breadth, you will get the answer to be 163.62 plus 1.6 percentage, which is equivalent to 163.62 plus 2.6 centimeter square. When this is rounded off, you will get the answer to be 164 plus 3 centimeter square. If a set of experimental data is specified to n significant figures, a result obtained by combining the data will also be valid to n significant figures. But there are certain exceptions. For example, if you are subtracting, that is 12.9 minus 7.06, both the data contains 3 significant figures. And according to the rule, there must be 3 significant figures in the final result also. But the final result is not written as 5.84 gram, but as only 5.8 gram, because the rules of addition and subtraction follows like this. We must retain only 1 decimal place in the final answer. The relative error of a value of number specified to significant figures depends not only on n but on the number itself. That is, for example, suppose if the measurement of mass of an object is given by 1.02 plus or minus 0.01 gram and another measurement is given by 9.89 gram. In both these data, you have got an error of plus or minus 0.01 gram. But if we are calculating the relative error in 1.02 gram, we get it to be plus or minus 1%. But the relative error in 9.89 gram comes out to be plus or minus 0.1%. So, though the number of significant figures and errors are the same in the given data, it depends on the data also. And an important point is that if we have multi-step calculations, then before the final result, in every intermediate step, we must retain one extra significant figure more than that is required. And the final answer only must be calculated to the correct number of significant figures in order to avoid errors. Hope you have understood the session. Thank you, dear students.